Okay, so here you see what I was alluding to in class before. This is from chapter 1, so figure 110 in the course book. And indeed, what you can see, this is a real radio continuum emission from the Orion Nebula. Now, the Orion Nebula is, well, you might have heard about Orion's belt. That's the that's part of they lie, the stars associated with the belt lie in the Orion Nebula. Okay, it's a massive young star forming region, and since these newly formed hot massive stars they're very hot on the surface, as we've discussed, right? So they emit a lot of radiation, and associated to them, this radiation then blows these photoionized bubbles around them. And those bubbles then are what we call the H2 region, or ionized nebula. And here, this is the one that is associated then with the Orion star-forming region. Because again, it's only in such star-forming regions where we find these young hot massive stars, because otherwise, you know, they live fast, they die young, so they're all gone now. For example, we don't have anybody close to us. Anyway, now in this radio, yeah, you see here, indeed, exactly what we have. This is the observation. So this is the frequency space. Now put in megahertz. So this is actually associated with radio emission. Yeah. So again, be aware of your units. It depends on whether you want to put this in lambda or in nu or in whatever. Just depends on the purpose. Huh? Here you see that this is actually the output intensity associated with this. But again, the radio astronomers, so they have chosen a weird unit, which I'm not such a fan of. But okay, that's their decision. What we want to focus on here is that we see this exact shape. Huh? We see this, that in the optically thick region, as we explained, this goes with the source function to nu to the 2, right? So essentially, the source function or Planck function here is associated with nu, and you see this power law rise in frequency until you hit this, and then you hit the plateau. These are the data points. Yeah, this is how it looks in reality. Of course, it's not. You know, this one is more than 1 sigma outside the theta, and then you have this, and this in our model was a plateau, right? It was 0, so it goes like this. Here it actually goes with 0.1, and that 0.1 is the quantum mechanical effects from this Gaunt factor that we neglected. So if you were to now just do a very simple radiative transfer model of that, which you could do with a very simple script, then you would find this and you would fit data, and then it would be like a straight line here. But regardless of that, you see that even if you wouldn't fit it, you get this transition, right? And that's pretty clear, even if you can't fit. You can actually just see that there is a transition here, I hope, from one slope there to this new square, right? Now, that we know is associated with an optical depth that is about unity. Because that's when it goes from being optically thin to optically thick. Okay? So it turns out, in order to get an estimate now of the density associated with these observations of the nebula, yeah, we don't even need to do this type of detailed model, which probably they have done here in this, yeah, where they have solved the full transfer equation, perhaps not even assuming a homogeneous medium, I don't know. Okay? But we can actually get a decent fit directly, which hopefully now then will also give us some general astrophysics insights to be further discussed. So let's see if we can actually do that. So we're gonna need the full expression, including the numbers now then, to do this, of course. So I put out the alpha nu free here with the actual, you know, numerical factor in there, and then, yeah. And then we're going to assume that this indeed is a nebula, like in the picture, and that nebula has an associated temperature with it, which is 10 to the 4, so 10,000 Kelvin. And that's like a reasonable estimate for the temperature in an ionization bubble. Again, it cannot be too low, because then it's not ionized anymore, right? We're going to say that this occurs at 300 megahertz, which I'm not sure whether it actually corresponds to the transition there, but perhaps it's not such a bad. It depends, of course, on the physical situation, right? And then we're going to have then we need to associate the length scale with this nebula. And now that we need some other estimates for, huh? This is likely a little bit overestimated. I just took it to be 10 parsecs. So essentially what you need to do is that you need to take an astronomical image, resolve the nebula, right? Measure the angular diameter or something like that, and then get, if you have the distance to the nebula, you have the angular diameter, then you know that you actually get the physical size of the nebula. Something like that, okay? This is the Orion, so here we have good estimates. This, for this emission, is probably a little bit too high, but anyway. It serves our purposes here. Okay, so we're going to say that that's 10 parsec. All right, and then we're going to say that this is where we can call it the knee, right? But then we know that the optical depth of this nebula is just alpha nu free, right? dl, okay? If we assume that this is homogeneous, we can just take it outside. So this is just the length then. And then we say this knee happens at roughly optical depth tau nu of unity. Because at unity, you will get this sort of transition. Usual, we use the radiative transfer equation. So we're going to consider the simplest, you know. We have some gas cloud here, which is emitting this. We're sitting here, yeah. But we're going to say that this is just a slab, okay? So it's not a bad approximation. And we're going to say that it's not backlit, which means that I nu 0 is 0, okay? And then we're going to assume that this gas cloud has a constant temperature T. And also, for simplicity, a constant density. Yeah, but we'll see that later. Yeah, okay. Now, for that situation, and since the emission here, processes here, is dominated by thermal bremsstrahlung, well, we already know the solution to the transfer equation. So the emergent intensity that we will see here, we know. It's just I nu e equals to I nu 0, yeah, e to the minus tau nu, where tau nu now is the associated optical depth with this cloud, plus S nu 1 minus e to the tau nu. This is the solution of the radiative transfer equation through a homogeneous slab, which we have had several times and which is actually also even, I think, given for you in the course book. Very convenient. But we already said that it was not backlit. Remember, we looked at other examples of this where we had backlit and we could explain various emission and absorption lines, etc., etc. Now we're not backlit. Yeah? And then we can see that, okay, our I nu emergent is going to be S nu, but S nu we know. That's the Planck function. So the Planck function at temperature T, right, for a given frequency now. And then 1 minus e to the minus tau nu. And that's all that there is here. So let's look at the two cases. Let's look first at tau nu much, much greater than 1. So we're going to go back now and do the things that we have done. And we're going to assume right from the get-go that we're in the Rayleigh-Jeans scale. Yeah? And then we're going to look for a given temperature, what's the shape? That is, what's the frequency dependence of the emergent intensity? Well, in this case, it's just the Planck function, right? And the Planck function, we know, but we have assumed that it's in the Rayleigh-Jeans scale. So then we know that it's just going to be proportional to nu squared. Yeah? But what happens now when at some if the optical depth at that given frequency is much, much smaller than unity. Okay, what happens then? Well, I nu then, emission, is just going to be approximately B nu, tau nu. That's from our normal Taylor expansion. Yeah? Let's Taylor expand that. So B nu we know. Tau nu is our extinction coefficient times the length of the slab. And now we make the assumption that, again, it's a homogeneous slab, which means that for a given frequency, the temperature is constant, right? But we're also going to say that the densities are constant. Okay? Which sometimes is a good and sometimes is a poor approximation. If it's a poor approximation, you need to do the integral. Huh? That's just how it is, numerically, normally. But now we're going to assume this. And then this is approximately just 8 nu times the length of this slab, or of the cloud, astrophysical cloud. Okay, but what frequency dependence does this have? Well, we did that there, right? Nu to the minus 2. Okay? So, now we look that I nu emergent in this, right, is going to be nu 2, nu minus 2. So it's frequency independent. That is, whenever the slab transitions from being optically thick to optically thin, we're going to switch the frequency dependence from this to this in the emergent radiation. Now, in practice, what does this mean? Well, we can just look, when does this happen then? Well, for a given slab, right? L doesn't change, okay? And we said that these are changed. So what changes the optical depth? Well, it's just the frequency, right? So for higher frequency, this goes with 1 over nu squared, right? So again, for the higher the frequency, we can see the the higher the frequency, right, the lower the optical depth. And the lower the frequency, the higher the optical depth, because it's an inverse relation. So if we now sketch the behavior of what we will have, it goes like this. We can have something like log frequency here, and we can have something like log intensity in some unit there. Yeah? Then it will, once it's optically thick, it will have this dependence. But then when it, at some frequency, it will transition from being optically thick to thin. And then it will just change the slope. So it will go from being essentially a nu power to essentially a nu zero. If you have the Gaunt factor in there, it's typically 0.1 because that's the quantum mechanical effect. But that's a very small difference between 0 and 0. So first off, you can look in chapter 1. There is an old astronomical spectra in there, which plots thermal free emission from an ionized region. And indeed, you can see this characteristic shape, which we have actually outlined here. Huh? Now, you could even do this yourself by setting up a little in your plotting program. I do this sometimes. Solving this equation, yeah? You know, just calculating the optical depth, plugging in the average, and doing that for a little bit of a frequency array. And then you take your frequency arrays there. Yeah? And then you will see that what indeed comes out here is shift. And depending on how you vary the number densities, the temperatures, the length of the slab, this will, of course, be shifted here and there. Yeah? But this will always be there. So we're going to take a little break now, and afterwards we're going to use this, that this is a generic feature of thermal bremsstrahlung, to actually get an estimate what the densities of such nebula are. Okay. Okay? Tau nu. Now, what do we have then? Well, we just have that the 3 times 10 to the 8, okay, times the number of electrons, the number of protons. We're going to assume that it's a hydrogen nebula times T to the minus 1/2, nu to the minus 3, and then we have this factor. But again, we can assume that we're in the Rayleigh Jeans tail, so we just get out this, right? And this we're just going to set to unity. Okay. And then it's this factor to worry about, but then we know if we assume that it's a hydrogen nebula in which all hydrogen is ionized, we know that the number of electrons, of course, must equal the number of protons. This is the same assumption we made when we made the calculations for the early universe. Remember? We made the calculations for the early universe and the recombination by assuming a hydrogen universe. Here we're assuming a hydrogen nebula, which is the dominant component. So then you can just solve for the number density here, the rest of known quantities. So the number of electrons squared is just going to be, you know, in this case, T to the 3 1/2 nu squared K, Boltzmann's K, Planck constant there, 3 times 7, 10 to the 8, and then the length. Okay. So now again, we're done in terms of estimating the electron density. Yes? The L vanished and should, of course, be there. Yeah, thank you. Very nice. Yeah, I missed it. It's here. It magically reappeared. So, yeah, that tau nu is 1, because we know that this, I'm gonna, for those of you watching online, I still have the same, although I walked over to the blackboard, we have the same on the blackboard. We know that, I said that this knee, and with the knee, I meant this, like the knee region, happened at 300 megahertz approximately. Now, we associate that knee region in the emission with the transition from being optically thin to being optically thick. But what's that definition? Well, it happens at tau nu approximately 1. So by calculating this at tau nu 1, we get an estimate, and it's only an estimate, but it's something we can do on the blackboard analytically, right? Which makes it very neat. It's actually not so bad either. It turns out to be better than one can expect from just, you know, how many assumptions we actually build into this. Huh? So now we can just plug in here, and of course we have to normally, as always, we have to take care of the fact that this was given in megahertz, this was given in parsecs. The Planck's constant needs to be given in the same units. So keep that in your head, that that's, if you are given a numerical exercise here, you need to do the correct unit translations. Otherwise, your numerical factors will come out way off, yeah? And that, if you get that, what I do expect, I say, and for example, like an exam, when you do it, it's not always, because I know that I also can do, but if you get an estimate where the density of the nebula is higher than the density of the room in your classroom, then you should be a little bit suspicious that you did a calculation error. And then you should say that, so to say, look, this does not sound reasonable. Similarly, if you get that the average density of the universe was as high as the density here inside the classroom, then it's a similar type of situation, or vice versa. That type of common sense in your order of magnitude estimates are actually more what I'm looking for than getting, you know, the 3.7 right. That's not the point here, okay? Just to give you a little bit of hint what I'm looking for with these type of exercises. So when we plug this in, then we get that the number density here is on the order of 400 per cubic centimeters. And that's, we can say immediately, it's not very high at all. It's actually, if you compare to the real, it's a little bit of an underestimate, which in this particular case comes mostly from this estimate. We should give this a little bit lower, but it's okay. Now, often what we want to do is that we want to associate this with the mass density, because those are the numbers we have better in our heads. Yeah? Hopefully. So the mass density, of course, is the number density of electrons times the mass of the electron, right? Well, no, plus the number density of protons times the mass of the protons. But since these are the same, this is just Ne times the mass of hydrogen, okay? Now, the mass of a hydrogen atom, so this is then 400 per centimeters cubed times the mass of the hydrogen atom, which is, look at knowledge in our course book, is roughly then 7 times 10 to the minus 22 grams. Yeah. So by the end of the day, we, no, 24. No, what is, can somebody look up the mass of the hydrogen atom for me, or do I have to? Does somebody have the course notes with them? It's 24, right? No, 20. 27. In grams, it's 24. Yes, in kilograms, it's 27. And is it really a 7 there? Is it? No, it's not a 7, right? it just felt wrong when I wrote it. Yeah. Yeah. All right. We're gonna leave this as 1. Yeah, for now. 1.7. Okay. Thank you. 1.7. That sounds okay. Now, regardless of that then, even if we associate this with, we don't know if this was 1.7 or 2 or some, so we can approximate 400 times this as 1,000, right? So this is on the order of 10 to the minus 21 grams per cubic centimeters. Okay? So, the density in the nebula, which is a property of the interstellar medium, right? It's on the order of 10 to the minus 21 grams per cubic centimeters. You can do similar things to estimate also then the mass in the interstellar medium, etc., around there. Yeah? So we have now some quite fascinating thing, because remember in our application, we got that the density of the universe today, right, was on the order of, I think it was 10 to the minus 31 grams per cubic centimeters. On the other hand, we have also said that the density in our room, yeah, remember how frequently the particles were colliding in our room, yeah? That we know is on the order of 10 to the minus 3 grams per cubic centimeter. Yeah? Now, the density in a stellar atmosphere, we've also considered, that's on the order of 10 to the minus 10 grams per cubic centimeters. And in my opinion, by doing these type of estimates, yeah, you might not get the full precise numbers that you can do today by just plugging this into your computer program and then fitting the spectra, and out you get the number for the density of the nebula, right? However, I hope to convey to you, by doing these type of estimates that we've done in the course, you get an appreciation for the extreme scales that we are dealing with in astronomy in general and in this course in particular, where we're actually dealing with applications going from the complete universe itself on the order of 10 to the minus 30 grams per cubic centimeters to the interstellar medium, or the ionized nebula that you see these nice pictures, which has 10 orders of magnitude higher density, but still is 10 to the minus 21 or something like that. Then we go to a stellar atmosphere, which, you know, is 10 order of magnitudes higher still, but still 10 to the minus 10, as compared to the air in this room. So we're dealing with 30 orders of magnitudes in densities, but we can use more or less the same physical insights and techniques, and just basically what we're doing in the course is applied physics, right? We're using physics of various branches, you know, ranging from, frankly, you know, quantum mechanics to classical electromagnetism to radiative transport and kinetic particle theory, to gain insights about objects of these vastly different properties, which in my opinion is one of the real beauties of working with astronomy. It's also something which, in my own opinion, is impossible to get real used to. I still cannot say that I understand or that I can appreciate what the density in the interstellar medium is, you know. We can calculate it. I can have a grasp, well, it's 20 orders of magnitudes lower than the density in this room, but what that actually means, how rare it is for well, particles to exist there at the first place, is quite remarkable. But despite that they're so rare, we get these extraordinary emission features that we can actually observe with our telescopes. And that comes from this fact that they're so big. They're 10 parsecs, right? Now, try to calculate the distance from the Earth to the Sun in parsecs, and then you will appreciate the differences in scales that we're dealing with. And of course, for the background radiation, which comes from this here, right, is even worse, because, you know, you can think about the scale of the universe itself. Another way, of course, associated to this, which we have also done, is that, remember, in an analogous exercise, when we actually looked at line broadening, we also considered the interstellar medium. We said, like, look, the particles there are so vastly separated. And then I just took this number. Now we know why I took that number. We didn't then. And I said, yeah, if the density is so low, they collide once in every 1,000 years, right? And then we said, okay, the particles here, in this air, which, you know, it's, for us, it doesn't feel so dense. But still, they collided X number every second. And that X was many orders of magnitude, if you go back and look in your notes, right? So that's the difference that we're dealing with here, which again is quite remarkable, at least in my opinion, when one thinks about it.